Our essential question: how do you fit a set of points to the equation of a polynomial function? All right, so let's talk about polynomial functions and what they might look like on a graph and what this actually means. So these first four graphs that are given to you, they come from 4.4a. This is the first figure in your book. And it's basically models of position of a moving object as a function of time. Okay, so these are models of position of a moving object as a function of time. Oops, I'm off the screen. So for modeling position as a function of time, then your input is going to be, or your independent variable is going to be time. And then your output would be position or maybe distance from some initial starting point. Okay? And we consider that initial, or that reference point. Maybe that reference point is a river, maybe it's a tree, maybe it's a highway, maybe it's some point that we're passing. Well, that reference point happens when the distance from that reference point is 0, or when you're on the y-axis or the x-axis, so y being 0. Now, we know that we are, some parts of this, the rate of change is maybe less steep than other parts, okay? And the rate of change, again, is that slope, right? So if I do distance over time, well, my slope is really representing velocity or speed here, okay? So we can see here that we have a slowing down. Our rate of change is not as large as maybe the speeding up rate of change. So we could say that this is a decreasing slope. It's still increasing over time, but it's increasing less and less and less. Okay, so if we're slowing down, we see that our slope begins to decrease. And if we're speeding up, we can see that our slope begins to increase. So I'll just abbreviate there. Now, with the same idea, what happens when we flatten out? What happens when our graph flattens out? Well, what kind of slope is that? That's a 0 slope, right? So we've got a 0 slope here, which means that we stop for a period of time. Time is still going on, right? But my distance from anything is not changing at all. Therefore, I'm stopped. Okay? Now, again, if you think of, your reference point being when y is 0, on this one, right, we've gone away from that reference point, and now we're heading back. So this is where you actually have a negative slope. Okay, and then what if we start away from that reference point and get closer and closer and closer to that reference point until we pass it? So it's really important, again, anytime you're dealing with a polynomial function, label your axes, try and really understand what the x-intercepts represent, and then also thinking about the slopes and those critical points. Also thinking about concavity and points of inflection. So just as a reminder, point of inflection is where the concavity of the graph changes. So it's a point at which the direction of concavity changes. So you can see here this graph goes from being concave down, again where I could draw that tangent line on the top of it, to concave up where I could draw that tangent line on the bottom, and the point of inflection is right where it goes from concave down to concave up. And then this other graph shows going from concave up to concave down, point of inflection right there. All right, a cubic function has exactly one point of inflection. So you're going to change concavity exactly once. Okay, so I mean, any cubic function that you think about, for example, both of these are cubic functions. You could also draw a cubic function with a couple of critical points, right? So I could draw something that looks like this, let's say. Okay, and I've got concave down, going to concave up. I think point of inflection might be right around there. I abbreviate POI. So a cubic function is going to have exactly one point of inflection. That's because it has two critical points. Its x-coordinate is given by the formula in the box. So x equals negative b over 3a. So if you ever want to find the point of inflection, this is how you find the x-coordinate. That should be really, really familiar to you because the vertex of a quadratic function is given by negative b over 2a. So in a cubic function, this point of inflection is given by negative b over 3a, cubic being 3, right? Degree of 3. All right, so we have a cubic function f contains these points, 4 different points here. And find the equation for f algebraically. And we're not going to worry about cubic regression. That's not something we're going to cover. Okay, so we'll check it basically by using your book if it asks you to check by cubic regression. So we're going to find this equation for f algebraically. All right, well, let's see. A cubic function is going to have, the standard form of it is going to look something like this. So I've got 4 things I need to find, right? A, B, C, and D, which means I'm going to need 4 separate equations, okay? So using my first point, I'll have 38 equals A times 6 cubed plus B times 6 squared plus C times 6 plus D. So that's one of my equations. Next equation, using my second point, 74 equals A times 5 cubed plus B times 5 squared plus C times 5 plus D. Okay, using my third point, I'll get my third equation. 50 equals A times 2 cubed plus B times 2 squared plus C times 2 plus D. And my last point will give me my last equation. A times negative 1 cubed plus B times negative 1 plus, squared, plus C times negative 1 plus D. Now, you could try and use systems of equations and do some crazy stuff. I think it's going to be way easier to use your matrices. Okay, so creating a coefficient matrix. I'll start that over here. So my coefficients of A, B, C, and D. All right, well, 6 cubed is going to give me 216. So I'll do the A's first. 5 cubed is going to give me 125. 2 cubed is going to give me 8. And negative 1 cubed is going to give me negative 1. Moving over to the B's. So I'm going to have 36, 25, 4, and 1. Moving over to the coefficients of C. I'm going to have 6, 5, 2, negative 1. And then all of the coefficients of D are just 1. Okay, line that up with the letter that these numbers are coefficients to. So these are A, B, C, and D. So that if I multiplied row by column, I'd basically end up right back where I started from. And then you want the constant matrix, which are over on this side. So I've got 38, 74, 50, and 80. All right, now, how do I get because I'm trying to solve here for A, B, C, and D. So how do I get this, this matrix by itself? Well, I need to multiply both sides by the inverse of this, right? So basically, I know then that A, B, C, and D will equal this matrix times the inverse matrix. The inverse of that. So bringing out my graphing calculator, I'm going to need to set up my two matrices. So my first one will be a, let's see, how about a 4 by 1? And that's going to be 38, 74, 50, and 80. Okay, my second matrix, is going to be a 4 by 4. Okay, and then when I do my work with this, I really need to think now. So I've got a 4 by 1, and I'm going to multiply that by a 4 by 4. That's not going to work, right? What if I switched them around? So this right now is my A, and this right now is going to be my B inverse. So I should probably instead go B inverse times A. Does that make sense? Because then what I'll have is a 4 by 4 times a 4 by 1. That'll be okay, right? These match, and I'll be left with a 4 by 1, which is exactly what I want because I want the A, the B, the C, and the D. Okay, so when I do this, I need to do B inverse times A. So I'm going to take that one, do the inverse of that, and then I'm going to multiply that by A. And I end up with -2, 15, 19. So A, B, C, D ends up as -2, 15, -19, and 44. Okay, so those give me those coefficients, which now I can rewrite, or I can write my equation as f of x equals -2x cubed plus 15x squared minus 19x plus 44. And there's my function. Okay, and then you can verify it by plotting and tracing the graph and making sure, or you could even use your table function, make sure that these points are actually on there. I'm going to let you go ahead and do that. And then we'll find the x-coordinate of the point of inflection and show it agrees with the graph. Okay, so I'm going to go ahead and skip to C. So B, you're going to use your grapher to make sure that you get some of those points. And then C, we're going to figure out our point of inflection, or the x-coordinate, which is going to be negative B over 3A. Okay, so let's see, negative B is going to be negative 15 over 3 times negative 2. So I'm going to have negative 15 over negative 6, which really becomes a positive, let's see, 5 halves, or 2.5. Okay, and then we're going to graph that and make sure that that's actually accurate, or looks to be accurate. So I guess I do need to plot this in here. Let's see here. There we go. Okay, so looking where I go from concave up to concave down is going to be somewhere in this region. So I'm just going to trace my graph. Oops, too far. And I can see there around 2.4, 2.5, that's basically my point of inflection where it's changing direction of concavity. All right, next page. I want to talk about this property. I'm going to kind of skip down here. The property, the constant nth differences property. So you'll remember with quadratics, you could, if you were given a table of data, you knew it was a quadratic function. If the inputs had a constant difference, similar to this one, right? This is going up by 1, by 1, by 1. And then let's say I was here, and all of the second differences were the same. Okay, so that was quadratics, if you remember that. Well, now we're into higher degree polynomials. So let's look at the cubic function. So the cubic function has what we would call a constant third differences pattern. So again, we have this constant change in our inputs, and then our outputs, well, you know, the first difference is not the same. The second difference is not the same. But when we get to the third differences, then we see that they're all the same. They all decrease by 12. So that's for this function right here. Okay. So you can say really for any nth degree polynomial function, if the x values are equally spaced, so they have that constant difference, then the f of x values have a constant nth difference. So if it was the 5th degree, then you'd go out 2 more branches here, and you'd have the same difference in that 5th row, or 5th column, I should say. Okay, so we're not even going to apply that, but just so that you know that, so that if you ever do get a set of data, you could look at it and ask yourself, all right, well, let me see if there is a constant 2nd, 3rd, 4th, 5th, 6th, 7th difference. We're going to do something that's a nice review from Algebra 2. We're going to find a specific equation of a cubic, a specific equation of the cubic equation having these roots. -1, -2, and 2, and passing through this point. So hopefully you remember that any root can also be written as a factor, right? So x equals -1 can really be written as the factor, right? We just bring this over, set it equal to 0, x plus 1. Okay? So what I'm going to do is I'm going to create a cubic with these three factors. But I'm also going to have that stretch factor out there, that a. Okay, and so my factors are x plus 1. This is x equals 2, or x equals -2, so that would be a factor of x plus 2. And then this is x equals 2, so that would be a factor of x minus 2. Now I need to figure out what a is. Okay, well, a can be found by taking this other point and plugging that in. So I've got -12 equals a times 1 plus 1 times 1 plus 2 times 1 minus 2. So I get -12 equals a times, let's see, this is going to be 2 times 3 times -1. So -12 equals -6a, or a equals 2. All right, so writing out my full equation, I have y equals 2 times x plus 1. Now, I'm going to go through and multiply. I see a difference of 2 squares here. Or sorry, a sum and difference pattern, which would give me a difference of 2 squares. So I'm going to go ahead and multiply that out, which will then give me x squared minus 4. And I'll continue to multiply this out. So I'll take that 2 and distribute it. Again, order doesn't matter with multiplication. I always like to combine or multiply my sum and difference pattern because I know it's going to give me a difference of 2 squares, which makes it pretty easy. And from there, I'll just go ahead and double distribute. And I'll rewrite it in descending order of degree. And there we go. That is one equation for this cubic equation having those roots in that point.